So just check it. My screen is visible or not. Is it there?
Yes.
Okay. Okay, so yesterday I explained somewhat the basics of that SMPS. I given one example, and that example is nothing but our mobile charger, right? So that is the best example of SMPS, right? So basically how that SMPS works, or what is the basic functioning, or how we can achieve that somewhat lower DC voltage converted from very high AC supply without any step down transformer, all that already I explained yesterday, right? So we taken that example, if 230 volt AC means if it is directly rectified and the obtained DC, it comes as 207 volts. So by using somewhat switch, if it is turn on and turn off momentarily, then the obtained output is like we can say pulsating DC, and the average of that pulsating DC, it is nothing but our expected output, and that expected output, it depends on the switching frequency as well as turn on and turn off time of that switch. Okay, so see, is it visible properly my screen?
Yes, sir.
Okay, so the same example I taken here also, you will observe there is one switch connected in series with the supply voltage. That supply, this Vs, it is nothing but DC voltage. Okay, so by switching the switch, that means turn on and turn off, there will be a voltage across this R. When that switch will be closed, the same voltage will appear across this resistor R. That resistor R I am considering as a load right now. So uh, that switch, if it is closed for time period T1, yesterday I taken it as a T on and T2 as a T off. Here, just correlate it to the repetitive period for that switch. It will be capital T equals to T1 plus T2, right? Already we covered, so we're not going on to waste much more time over here. So this is the nature of obtain output voltage Vs during time period T1. As the switch will be closed, the same Vs will appear across this resistor R, and when switch will be open, that path will get open circuited, and hence no output across that R. Is it? So the same waveform is shown. See, T1, it is nothing but on period of that switch. T2, it is the off period. Okay. Now, how much will be the current, output current? It will be simply the available output voltage divided by the resistance of that resistor, that is R. Okay. So the second waveform, it is shown for current. You will observe its amplitude whenever there will be availability of output voltage across that R, then and then there will be non-zero current. Otherwise, when voltage will be zero across that R, current flowing through the R also will remain zero. And that total time period is shown as capital T. Okay. Now, mathematically, yesterday I given that formula directly, that VO equals to capital D times of V in. If you remember, just try to recall it. Same uniform, I again repeated over here, and the average output voltage, that VA of this pulsating DC, right? Average of this pulsating DC, it can be determined by taking the integration of the available pulse amplitude, right? And that's why the period is, as the period is capital T, so the average value VA equals to 1 upon that period, that is capital T, integration 0 to T1, okay, of VO dt, right? So see why that integration is taken from 0 to T1 only, not 0 to T2, because during time period T2, as the output voltage it remains 0, so no need to consider it, and hence that integration is taken from 0 to T1 only, because whatever average output voltage we will obtain, that will be during time period T1 only. During time period T2, as the voltage remains 0, so no meaning of its average, it also will remain 0, and hence that output voltage for 0 to T1, how much it will be, as already I told, whenever that switch will be closed, the same source voltage will appear as output voltage, right? That means VO is equals to VS for time period T1, and that's why I replace that VO by VS dt, and when you will solve it, you will have the answer as T1 by capital T into VS, okay, as that Vs is a constant. Okay, so that capital T, it is nothing but what? It is T1 plus T2, or we can say T on plus T off, right? And yesterday I written that formula, capital D is nothing but duty cycle is equals to T on divided by T on plus T off, right? That T on is nothing but T1 over here, and T on plus T off is nothing but capital T, correct? So you can replace this 1 by capital T as F, as the frequency is nothing but reciprocal of time period, right? Now that one cycle, that is capital T. So I can write the same formula as F times of T1 into Vs. Got it? That capital T is nothing but what? 1 by F, and hence 1 by T is nothing but F. So that F into T1, or if you are getting confused, simply you just remember this one. That small T1 divided by capital T is nothing but what? T on divided by T on plus T off, and that is the duty cycle. Here I written that duty cycle as K. Yesterday I mentioned it as a capital D. You can write anything, no issue. So this VA is nothing but the average output voltage of this pulsating DC, and that is equals to K times of Vs. Or you can write capital D times of V in. Vs is nothing but what? Supply voltage, right now, Vs. Similarly, average value of load current, you just divide it by that the load resistance R. That means IA will become VA equals to IA equals to VA by R. We got that VA equals to K times of VS, and hence it is K times of VS by R. That's all. Already I mentioned what is that K and what is that F. All right. Now about how to turn on and turn off that switch momentarily right now. So you will observe there are two waveforms. One is somewhat trapezoidal or sawtooth waveform. We can call it as a sawtooth also, and another one is a straight line. Okay, that straight line I mention it as a VCR. That means carrier, and this sawtooth waveform, that is a reference. Or you can call that straight line as a reference and sawtooth as a carrier also. No issue. Right. So these two waveforms, these two signals, when you will going on to apply somewhat comparator circuit, that also we will going on to study in detail when that OPAMP part will start and its applications. Okay. So at this stage, no need to worry, because by taking the same example, I will going on to show you how that pulses gets generated by using a OPAMP as a comparator. Okay. So simply you will observe when that reference waveform, that is sawtooth waveform, is less than, in terms of its amplitude, is less than the carrier amplitude. Carrier amplitude is constant. It is a constant DC signal right now. While that sawtooth, it is time varying signal. See, so you will observe for time period 0 to up to over here. Is it visible to all? My cursor. For time period 0 to up to over here, if you compare the amplitude of these two signals, you can say that carrier signal, which is a straight line, have much more amplitude as compared to that reference signal or sawtooth signal. Okay, and when such type of two signals will be applied to the comparator, what that comparator will do, it will go on to compare that two signal waveforms, and which one is more dominant. Accordingly, it will go on to generate its output either as logic high or logic low. So in this case, you will observe for time period 0 to KT, it is mentioned as time period KT. Okay, so 0 to KT, the output of that comparator will remain logic high, at KT, as both input signals are equal in magnitude, that means over here, see, right? The amplitude of VCR and amplitude of this sawtooth, both will be equal. So when it will become equal, immediately the output of that comparator circuit, it goes to logic 0, and it remains 0 until again that reference waveform will have somewhat low amplitude as compared to the VCR, and accordingly that pulses gets generated. So this is just for your logic, how that transistor, if we consider the MOSFET, will be going to turn on and turn off, right? So the switching frequency of that switch, that will depend on the capital T of these pulses, correct? Got it? Is it okay? It is somewhat theoretical part. Am I audible?
Yes, sir.
Okay.
Yes, sir.
So what is that SMPS? It is circuit which is operated by switching, and hence the voltage vary continuously. That means the output voltage right now, as we are obtaining that pulsating DC. The switching device, it is operated in saturation or cutoff mode. Now see, uh, actually, this statement, it is applicable to BJT, not for MOSFET, because MOSFET, if we prefer MOSFET, then we have to replace this word by ohmic region. Right now, the switching device, it is operated as an on switch, means what? That MOSFET, it should get force into its ohmic region, then and then it will be able to act as a perfectly closed switch. And whenever we want to keep it in off state, then it should work into cutoff mode region, right? But in case of BJT, there is that amplifier region is uh, different. That is the active region. If you can recall from your first year syllabus, then you will get clear idea about it, right? Then the output voltage, it is controlled by switching time of the feedback circuitry. Already yesterday we taken that example. If that output tries to go down, that feedback circuitry, it will go on to sense it, and the action taken by the that controlling circuitry, that is to increase the pulse width so that the output will get retained to its original value. Okay. So the switching time, it is adjusted by adjusting the duty cycle. Already I explain all these points. So there are various types of SMPS, like step up converter. Another name is converter. Huh? You have to remember this word. Okay. So step up converter, it is also known as a boost converter, or step down converter. It is also known as a buck converter, then forward converter, flyback converter, self oscillating, etc. Right. So out of these, in your syllabus, first two are mentioned, that is step up converter and step down converter, that is buck and boost. Okay. Now the electrical specifications, you should be just familiar. No need to go in detail through it, but you should have the knowledge about that electrical specifications. I think you already you might have, because you are using mobile, and the ratings of that mobile charger, it is already provided on that charger. That means how much is its output in terms of voltage, in terms of current, etc. And from that you can calculate how much is the wattage of your mobile charger, right? So see, various examples are taken. Rated output voltage of that SMPS, for example, 12 volt, 13, 14, 15, etc., up to 24. So these are the various, we can say, SMPS having different output voltage. Right now, all these are the separate SMPS. Huh? Then, if it is of 12 volt, then it will be mentioned on that charger like its rated current. Output current is 2.5 amperes DC. This rated output voltage, it is also DC voltage as well as it is regulated. So you can take any one column so that you will get understood it properly. Okay. The maximum output voltage. See, even if we are calling it as a regulated power supply, but still, due to variation in either load current or variation in supply voltage, as practically the percentage load regulation expected is 0%, but practically somewhat will be there, and hence maximum output voltage, it is mentioned as 12.5. So if there is increase in supply voltage or decrease in load current, then that output voltage may get rise from expected, that is rated 12 volt to 12.5. Small change in output voltage may occur. Similarly, minimum output voltage for the same, this first column, I taken the first column for the explanation purpose. So minimum output voltage, if there is decrease in supply voltage or if there is increase in load current much more, then the output voltage may get down to 11.5 from its rated value as a 12. Correct. So how much is the delta VO here? We can say it will be from 11.5 to 12.5, even if it is rated as 12 volts, right? So the output voltage we will go on to obtain for this first example, that will be from 11.5 to 12.5. Then ripple and noise, that is nothing but unwanted quantities which are available in the output. It should be zero. Okay, that ripple content or noise content in the output of any we can say regulated power supply, it should be, or it is expected as a zero, but in this first example it is mentioned by the manufacturer as less than 150 millivolts, right? So it is a one of the good type of SMPS, we can say, as that noise level as well as the ripple content, it is much more less. Okay, then overload current in ampere. So see, rated current is given as 2.5. Means what? We should consume the current from such type of charger up to 2.5. Expected is like this, right? But still, if short circuit occurs or if somewhat low resistive load gets connected across such type of SMPS, then up to how much current it can provide, that means above the rated value is 2.5, but still it can provide up to 4 amperes. But it should not be a continuous 4 amperes. Otherwise, it will be harmful to our SMPS. It may get damaged due to overcurrent condition. Okay. Then overheat protection. See, I taken this example from one of the manufacturer of SMPS, and that manufacturer mentioned the somewhat electrical specifications of the product. So all these are the various SMPS available by that manufacturer, and hence I taken it just as an example. Okay, then overheat protection. Yes, that manufacturer is saying yes, we provided the overheat protection. If that SMPS gets overheated, then auto shutdown occurs in their products, right? Then the rated power. Rated power means it is the output voltage divided by into output current. DC output voltage into DC output current. So it is 30 watt. So this first example, this is a 30 watt SMPS. Then switching frequency, or whatever the switch is used, at what frequency that switch gets switched, and that is by 132 kilohertz. Remember this one. So you will understood over here the switching frequency in SMPS. It is mostly it is kept somewhat at high value. Okay. Then the power consumes, how much power it will be going to consume when it will be going to deliver the rated power as a 30. So it will be, that means AC power. AC power, it will be less than 0.3 watts. And efficiency, last parameter, that is efficiency of this SMPS, this first example, 12 volt SMPS is greater than 83.7. Okay, expected efficiency is 100%. So see, efficiency means what? Whatever input you are giving and how much output you are obtaining. So if the, or we can say always, we can't achieve the output greater than input, correct? As well as practically we can't obtain output power exactly equals to input power, because there is some losses across that number of devices which are used over there, right? So by considering that losses, efficiency obtained, that will be greater than 83.7 in this example, right? So is it clear about these electrical specifications? After my lecture, you just check your mobile charger. Everything will is generally given on that charger, how much its input voltage you can apply, right? That means AC supply, which to which you can plug your mobile charger. that is AC rating, and how much is the output of that mobile charger. That is the best example. Okay, and that is nothing but the electrical specifications of SMPS. Now we'll see about that first type, that is buck converter, that is step down converter. First type of SMPS. Already I explained the working principle of SMPS by taking the same example. Only few components are added over there that I will go on to explain. So see again, for the shown circuitry, input is Vs, that is DC voltage, high DC voltage we can say. Then there is a switch, MOSFET acting as a switch, which is connected in series with that supply voltage and output or to the load. Okay. Now this concept already you are familiar. Whenever this switch will get turn on and turn off, accordingly we will be able to obtain the pulsating DC over here, right? Now see these two components. There is one inductive coil or inductor, we can say, connected in series with that switch. So whenever switch will be closed, there will be a flow of current like this from source. This Is is shown. As we are considering switch is closed, that means through the switch that current will be going to pass through this inductive coil and then will appear across this R, correct? So whenever that current is flowing, this inductor, it will going on to store the energy, or it will get charged up, right? It will store the energy with the polarity as shown by that red color. Okay. Now when that switch is closed, we can say this diode, it will be open because its cathode will appear at the positive potential which is applied through this switch, is it? So diode will be in reverse bias condition and hence will be going to act as a open circuit. Similarly, when that switch will be closed, as current is flowing through this inductor, that inductor will going on to store the energy. At the same time, this capacitor also going on to store the energy, right? As well as the load also will get power. So see, over here, if you consider this node, incoming current is considered as I, that is the inductor current, and outgoing currents are 2, that is IO provided to the load, and another one is the capacitor to get charge, right? Now when switch will get open, what happens? As you are already familiar, whenever current flowing through the inductor gets stopped, the energy stored by inductor and its polarity, it gets reversed. I already explained it. I think whenever I taught that tank circuit, LC circuit, I think it is not there. Okay. So see, this is the property of inductor. When current flowing through the inductor gets stopped, immediately the store energy polarity, it gets reversed. That means this negative will appear towards LHS side and positive will appear over here. Correct? So when such type of polarity reversal will occur, you will observe this diode, it will become forward bias because from this end, the switch is considered as open now. As the polarity gets reversed, means negative will get applied to the cathode. Correct? So this diode will get turned on and the store energy, it will get free wheel over here like this. So the obtained output, it will be again somewhat pulsating DC, and its average voltage, already just we discuss about how much will be the average output, and that will be capital K times of Vs, right? That means it will be less than input. And that's why we are calling it as a buck converter or step down converter. A large DC voltage gets converted into a small DC voltage. That's why the word is given as a converter. Okay. Then the next one is boost type of converter. Boost means a step up converter. Here you have to remember the output voltage, it will be greater than input voltage, that is Vs. So how it will be possible? See the working. Only the position of that switch is change. Switch and these two components. Now that inductor, it is kept in series between load and source before the switch is connected. Okay. So just imagine if the switch is closed, what will be going to happen? This inductor or this path, it will get completed over here, and it will be a somewhat low resistive path as compared to the next one, that is through diode and the load, then capacitor, etc. So when switch will get closed, at that time this inductor current, it will be want to flow through the switch like this. It will get charged up positive towards its LHS and negative polarity towards its RHS, right? Somewhat charge that inductor will going on to hold when that switch will be in closed condition, right? Now, the consider the next condition, this switch gets open, right? Whenever this switch will get open, what will be going to happen? The current, it will now start to flow through the diode because there is no option for the current over here. But in this case, you will observe the whenever current will be going to flow through diode, there are two voltage sources available in that path. One is the main source voltage and another one is the charge held by this inductor. Okay, so these two will get add with each other and then it will appear as output voltage. Is it clear? For example, suppose this Vs is 10 volt, right? Initially the switch is closed, inductor was initially it was totally discharged inductor. When switch is closed, inductor will start to get charged. Suppose it gets charged to 5 volts. This is the charge stored by inductor, equivalent to 5 volt. When this switch will get open, at that time, the total available input supply, which will get forwarded to the load, it will be main source voltage that we consider as a 10 volt plus the charge held by inductor, it is 5 volts. So the appeared output voltage, it will be equivalent to 15 volts. And that's why it is known as a boost type or step up type of converter. Is it okay? Shall I go ahead?
Yes, sir.
Okay. Now we'll see advantages and disadvantages of SMPS, and then later on we'll go on to compare it with our LPS, that is linear power supply. Okay. Linear power supply means whatever the linear regulator ICs we studied, like 78 series, 79 series, LM317, 337. By using that linear regulator IC, we can design and develop the regulated DC power supply. By using SMPS technique, also we can obtain the regulated output. Okay, regulated DC output. So both are the regulated DC power supplies, remember. Okay. Now the advantage, the switching action means the series regulator element is either on or off. Very high efficiency levels are achieved as very little energy dissipates as heat across switching transistor. Okay, so see, this is the main advantage of SMPS over that linear regulated power supply. Across that linear ICs, I already explained 2 to 3 volts drop is always there, and that's why we are calling it as a high dropout voltage regulators. But in case of SMPS, as if we consider that switch as a MOSFET, whenever the MOSFET will get switched to its ohmic region, being a closed switch, then the resistance offered by that MOSFET is very, very small, almost 0 ohm. Okay. For example, if you try to download the datasheet of one transistor MOSFET, you can note down it, that is IRF540N. This is the number of that MOSFET, IRF540N. So its RDS on by the manufacturer, it is given as 0.04 ohm only. That means whenever this switch will get closed, a very low resistive path it will go on to offer, and hence as the resistive path is very low, we can say the voltage drop across that switch, it will be few millivolts only. Okay, and hence as again I already explained, efficiency is nothing but the output power divided by input power plus power dissipated, right? Now, so as power dissipated power increases, the efficiency of that system it gets degraded, and hence in case of LPS the efficiency is somewhat less as compared to this SMPS technique, right? As a result of high efficiency and low level of heat dissipation, the switch mode power supplies are very compact. See, already I given the example of our mobile charger. As it is, we are converting from 230 volt AC to very small DC voltage, just like we can say 5 volts. But the size of that converter, which we can call it as a SMPS, is very, very small. Okay. Then SMPS technology also provides high efficiency voltage convergence in voltage step up. Okay, in both cases, that is step up and step down, that is buck and boost converters. that high efficiency is possible, right? But there are few disadvantages also. The transient spikes due to the switching action can migrate into other areas of the circuits if not properly filtered. So see, what is the meaning of these transient spikes? So just imagine there is a DC source, right? To that DC source, the switch is connected and that switch is momentarily turn on and turn off. What will be the effect on that source? Okay. Due to the high frequency switching of that switch, these transients, it gets generated in that stored energy. And if it is not filtered properly, then it can get migrate into the supply lines, right? So this is the disadvantage. These spikes can cause these can cause electromagnetic or radio frequency interference, affecting other nearby items of electronic equipment, particularly if they receive radio signals. So this, we can say, electromagnetic interferences or that radio frequency RF interference, it may affect the working of somewhat electronic equipments. Then the next one is, it is somewhat costly as compared to linear power supply, as well as the design is slightly somewhat complex as compared to LPS. Okay, so these are the few advantages and disadvantages of that SMPS. Now we'll compare it with the LPS. So the parameters, first column, second one is I taken it as a linear power supply, and then last one is the SMPS. Okay, so that parameters first, it is based on what? So the linear power supply dropout voltage dissipates lots of power. Then in SMPS oscillate switch on and off, so less voltage drop dissipates less power. Then input frequency in case of linear power supply, as we are not doing any switching action over there, so the input signal frequency, it is just kept as it is, that is 50 to 60 hertz. We are not changing it. Okay, but as that input signal frequency is low, there is need of high value capacitors for the filtration purpose. Okay, in case of SMPS, uh, as just we taken that electrical specification part, and over there you observe the switching frequency of that switch by that manufacturer is kept as 132 kilohertz right now. So in general, the switching frequency in SMPS technique, it is kept in kilohertz to megahertz, and that's why there is need of somewhat small value capacitors as a filter. Efficiency, already I told, as there is more dropout of power or voltage across that linear regulator ICs, the efficiency of LPS, it is only 25 to 50%, while in case of SMPS, in general, it is above 65%. Then load regulation, you will observe the SMPS is somewhat poor over here. Okay, that load regulation, it is 0.05% to 0.2% in case of LPS. But in SMPS, it is 0.05% to 0.5%. Similarly, line regulation, in terms of line regulation also, SMPS is slightly poor as compared to LPS. Then the ripple, RMS, in case of LPS, that ripple content is very, very small, just maximum possible is 5 millivolts. But in case of SMPS, again, that ripple content is also somewhat more due to, again, the high switching frequency and all that. Then size, in terms of size, SMPS is best. Then weight, again, SMPS is very lightweighted. Our mobile charger is very lightweight device. Then EMI, okay, so see, just in previous slide, I taken that point. If it is not properly filtered, then it will go on to generate the transients in the supply lines. So this electromagnetic interference, that is EMI, in case of LPS, it is not there as the switching is not done. While in case of SMPS, it is very high. Then the transient response, it is somewhat faster. LPS is somewhat faster as compared to SMPS. Then complexity, linear power supply design is somewhat less complex, while SMPS is more complex. So I think you might have studied this topic properly, and that is nothing but all these voltage regulators. I taken somewhat extra regulators as a content beyond the syllabus, that is 7.8 series and 7.9 series, and as per syllabus all the points are covered. So this is the points from your syllabus of this unit, third unit, right? So in this way our third unit is also completed now. Third unit is very small as compared to first two. Okay, and now I will switch to the next unit, fourth unit, and that is nothing but operational amplifier. Is it okay? Shall we go ahead? Are you there?
Yes, sir.
Okay. So, in front of you that objectives from this unit, by this unit, it is placed. So the course objective is to introduce you people the operational amplifier, then concept, parameters, and various applications. Then the course outcome will be you should be capable to build the circuits using OPAMP for various real life applications. Right. Now the syllabus for this fourth unit, it is given as block diagram of OPAMP, then differential amplifier, analysis for dual input balance output differential amplifier. That means here both analysis are mentioned in your syllabus, that is AC analysis using that R parameter and the DC analysis. Then the level shifter, this is one of the stage of that OPAMP. We will discuss in detail, don't worry. Then OPAMP parameters, then OPAMP characteristics, and OPAMP as a feedback amplifier, that is voltage series and voltage shunt, and the effect of on RI, RO, gain and bandwidth of that feedback. Okay, so already you covered the last 2 points in that feedback amplifiers. Only instead of using that MOSFET or transistor, that much part we will going on to replace by OPAMP, right? I think in your first year syllabus, that introductory part was there about the OPAMP. Is it there? That means, are you heard this word, operational amplifier, OPAMP word? Is it there?
Yes, sir.
Okay. So why this device is known as an operational amplifier? Because see, first of all, the key point is that it is a very high gain direct couple multi-stage amplifier. Now I think you are familiar with this multi-stage amplifier. I preferred this word during my one of the previous lecture whenever we were studying about that feedback amplifiers. Okay, so in that I taken the example of voltage series feedback amplifier by using 2 stages. Can you recall it? There are 2 transistors we taken, and the output of second stage, it is connected at the input of first, right now. So that amplifier circuit is also known as a multi-stage amplifier. So see why I'm saying all these things. You should be familiar with all these words. That's why. Okay. Then one more word is mentioned over here. That is direct couple. Direct couple means what? See, in that example, you will observe there is one common capacitor between the output of first transistor and input of second. Right? So the coupling between the 2 stages over there, it is done by using a capacitor. But in case of operational amplifier, OPAMP, again as it is a multi-stage amplifier, a number of transistors are there, a number of amplifier stages are there, and how these multiple stages are connected with each other. These are connected with each other by direct coupling. Means there is no any component For example, the output of first stage, it is directly given to the input of second without any component or through without any component. That's why it is known as a direct couple. Okay. Then the next word is very high gain. So you are already familiar with gain, voltage gain, right? Now if you consider simply a voltage gain, you can easily determine the voltage gain, that is output, obtain output voltage divided by applied input voltage, so that you can calculate the gain. So this operational amplifier, it is very high gain amplifier. See, by using MOSFET in our second practical, we obtain the gain of that common source MOSFET amplifier, CS MOSFET amplifier, equals to how much? Can anyone? Second practical. You already done it. That achieved gain was 30, if you can recall, 30. Am I right? 3 volt was the 3 volt was the output peak to peak voltage, and input we consider as 100 millivolt peak to peak, right? So the calculated gain for that MOSFET amplifier, CS MOSFET amplifier, was 30. But for this dedicated IC, that is operational amplifier, the gain is very high. For example, if it is 741, this is a general purpose OPAMP, 741, that number is mentioned over here. So it is known as a general purpose. So for this, even if this OPAMP is general purpose OPAMP, its gain is 2 into 10 raised to 5. Just compare it with our conventional amplifier, which we studied, through our second practical. Over there, gain was only 30, and for this OPAMP, how much is the gain? It is 2 into 10 raised to 5. That means 2 lakh is the gain, and that's why this word is preferred. It is very high gain. Got it? Direct couple, multi-stage amplifier. Is it okay about this sentence? Very high gain, direct couple, multi-stage amplifier. See, I will just show you. This is nothing but the functional diagram of operational amplifier. Is it visible to all?
Yes, sir.
So see, there is no any coupling component between various stages. Totally 4 stages are shown, and they are differentiated by that vertical blue colored dotted line. First stage, second stage, third stage, fourth stage, like this. Okay. So the first stage gets coupled to the next one without any component, and that's why it is known as a direct couple. Then multi-stage, more than one stages are there, and that's why it is known as a, or it is called as a multi-stage. And very high gain, because the open loop gain of this device, it is very high. I already given the example of that 741. The gain is 2 lakh, 2 into 10 raised to 5. Okay. So is it clear about this sentence now? Very high gain, direct couple, multi-stage amplifier, which is capable of carrying out mathematical operations like addition, subtraction, integration, differentiation, log, anti-log, etc. And that's why we are calling it as a versatile device, we can say. Operational amplifier. Is it? It can perform various operations, right? Mathematical operations, we can say. Okay. Now, you might have seen such type of device in your lab also. See that 741, it is 8-pin IC, right? All that stages, whatever I shown, they are inbuilt by using that semiconductor chip inside this device. Okay. And it is titled as a 741. So this is the best example, or we can say this is general purpose IC. So in that, as per the manufacturer, the pin configuration is like this. Pin number 1 not connected. See, before going to that, are you familiar from which terminal we should call it as a pin number 1? Are you capable to identify that pin numbers? Yes or no? Just let me know. It's okay. See, on that IC, you will observe such type of one notch. Okay. So the terminal closer to that notch is the pin number 1. And start it like this. Pin number 1, then 2, 3, 4, and directly switch towards its opposite side as 5, 6, 7, and come back to 8. That means towards the north side. Okay. So that pin number 1, it is generally not used. Then pin number 2, it is the inverting input. Pin number 3, it is known as non-inverting input. Pin number 4, that is for the power supply, negative power supply. That's why it is mentioned as minus Vs. Pin number 5, again not connected. Pin number 6 is the output. Pin number 7, this is for plus VCC or positive DC voltage for its operation. And again pin number 8, it is not connected. So its symbol is also same. See, inverting input, that is nothing but pin number 2. Non-inverting input, that is nothing but pin number 3. Output, pin number 6, plus VDC, pin number 7, and minus VDC or minus VEE, or you can call it as minus VS also, as pin number 4. Okay. Whenever we will going on to study in detail, you will get clear. So at this stage, again, don't mind about it. Okay. So before going to the next slide, I would like to just highlight over here what is mean by inverting input and non-inverting input. So just imagine to this IC, if I connected this non-inverting input, or we can call it as a positive input, to the ground. Okay, just ground it. Take one sinusoidal signal and connect it at the inverting input. Right? There is somewhat feedback path and all that to control its gain. Otherwise, it operates in saturation. How it operates in saturation or exactly what happens, that also we'll discuss later on. Okay. Now, if that sine wave is connected at the inverting input, we'll get the output as a sine wave, but there will be a phase shift of 180 degree. Got it? That means whenever input is positive half cycle, the obtained output during the same time period will be negative half, and vice versa. Or if we consider that input as a DC, again that non-inverting input is kept at ground. If I applied plus 1 volt as an inverting input, my obtained output will be minus something. Why I said minus something? Because that obtained output will be minus gain times of applied input magnitude. And that is 1. Okay. So what happens if we apply the input to the inverting terminal? The obtained output gets inverted, in short. Got it? And if I kept that inverting input to the ground and applied the input to the non-inverting input terminal, then the obtained output will be in phase. It do not get invert. Invert means what? To get change. It do not get change in terms of its polarity. Or in terms of phase shift, we can say there will be 0 degree phase shift between the applied input to the non-inverting terminal and the obtained output. Got it? Why these terminals are known as inverting input and another one as non-inverting input. Is it clear? You might have already studied it, but still, I just given that basics of that OPAMP. Okay. Now the block diagram of OPAMP. Already I shown that multi-stage. As it is a multi-stage, it is divided into number of stages as. See, this first stage, before going to that first stage, again that inputs are shown as non-inverting input and inverting input. You can show that plus minus as shown over here, or minus towards the upper side and positive towards the lower side. Only it should get titled properly. That means positive sign respective terminal, it should be a non-inverting input, and negative sign respective terminal, it should be a inverting input. Okay. So the first stage of this operational amplifier is known as input stage. Okay. As the inputs are connected directly to that stage, it is simply known as a input stage. Now this input stage is designed and built by using dual input balanced output differential amplifier. Now at this stage it looks somewhat complicated, but don't mind. Immediately I will be going to show you what is meant by this long title amplifier, that is dual input balance output differential amplifier. Okay. Then the next stage, second stage, is known as the intermediate stage, and it is configured by using again the transistors in such a way that it is titled as dual input unbalanced output differential amplifier. See, what is the difference between first two? First one is dual input balance output, and the remaining two words are common, that is differential amplifier. Second stage, again, it is a dual input and unbalanced output differential amplifier. Okay, when you will, I will show you the basic circuit diagrams for these differential amplifier, then you will get clear. Then the third stage is known as a level shifter or level shifting stage. Why it is preferred, that also I mentioned in the next slide. And the last stage is output stage. Okay, so that level shifting stage, it is emitter follower using constant current source. Now this word you already studied from the second unit, current mirror, constant current source, etc. Okay, so the emitter follower, that means here the example of BJT is taken. Emitter follower means what? The output is taken out from emitter, or we can call it as a CC configured transistor. CC configuration. The transistor is used in common collector configuration. Okay. And the last one is complementary symmetry push-pull amplifier. Again, it is somewhat to boost the current providing capacity of the device. That current providing capacity means we can call it as a sourcing capacity. It can source a sufficient current to the load. Okay. And to have that much capacity, mostly this output stage is preferred as by this configuration, that is complementary symmetry push-pull amplifier. See that input stage, dual input balance output differential amplifier with constant current source biasing. This is known as a biasing, constant current source biasing. Next one is intermediate stage. It is a dual input and unbalanced output. So see over here, I will going on to show you the difference between these two. You will observe, is it visible properly? See, for the first stage only, just concentrate on first stage. There are two transistors, emitters of both is common, right? And it is biased through somewhat this constant current source biasing. So at this stage, forget about it. Constant current source biasing, just concentrate on where the inputs are applied to these two transistors. For first transistor, input is given to the base. Then if it is called as a non-inverting input, then we know the another input is inverting. It is a dual input IC, correct? So second input is inverting input, and it is connected to the base of second transistor, right? So how many inputs are there? Two inputs. That's why it is known as a dual input. Or simply you can call two input. Now the balance output means what? The output of this differential amplifier, it is taken from the collector of both transistors. See, from first transistor that output is taken out from here, from second transistor that output is taken out from here, right? So how many output terminals are there? Again two. Okay, and that's why it is known as a balanced output. Output is taken out from the collector of both transistor. What is meant by dual input and balanced output? And Such type of configuration is known as a differential amplifier, and that's why that word is common, that is dual input balanced output differential amplifier. Now see, what is the meaning of differential amplifier? That name itself indicates differential amplifier means it will going on to amplify the difference between two inputs. So there are two inputs, inverting input and non-inverting input. Suppose one is, will give you the example. Suppose non-inverting input is plus 5 volt DC voltage and inverting is suppose plus 3 volts. So how much will be the differential voltage? It will be 2, difference between that two, right now. And this amplifier, that is differential amplifier, will go on to amplify that 2 volts. That is the difference between these two. Got it? And that output is taken out from the collector of both terminal and applied as an input to the second. Now switch to the second stage and just observe what is the input to the second stage. What is the input? See, for this first transistor of second stage, its input, that is base terminal, where it is connected to the collector of second transistor of first stage. Okay. Similarly, in the second stage, for second transistor, input, it comes from the collector of first transistor of first stage. So how many inputs are there to this second stage? Again, there are two inputs, right? And that's why this stage is also known as a dual input. But it is mentioned as, see, dual input, that word is common because for both stages, input terminals are two. That's why dual input. First one is known as a balanced output because output is taken out from the collector of both transistor. While for this intermediate stage, it is titled as unbalanced output. Why unbalanced output? Because from the second stage, output is taken out only from collector of one transistor. That means we can call it as a single-ended output. And hence it is known as a unbalanced. And the output of that single-ended output of the second stage, it is given as an input to the next stage, that is level shifter. Got it? Now I think you are very clear about these two types of differential amplifier. That second stage is also differential amplifier. It will go on to amplify the difference between two inputs applied to it, and that is nothing but output of first stage. So the difference, again, it will go on to amplify, and as it is a single-ended, that amplified differential voltage, it will go on to apply as an input to the third stage, that is level shifter. Is it clear about dual input, balanced output, dual input, unbalanced output, and what is meant by differential amplifier? Okay. Now, basically there are four types of differential amplifier. That is dual input, balanced output, or we can call it as a dual output also. See, I mentioned over here. Differential amplifier, there are four types. Dual input, balanced output, differential amplifier, or dual input, unbalanced output. Unbalanced output means what? Single output or single-ended output, differential amplifier. Third type is there, that is single input, balanced output. That means there will be a single or one input terminal while the output is dual. Okay. And last one is single input and unbalanced output, means single input and single output. The respective circuit diagrams I highlighted over here. Is it visible properly? See, this first one, it is dual input balanced output. Two inputs are shown, VS1 connected to the base of first transistor, VS2 connected to the base of second transistor. And VO, it is mentioned between collector of both. That means across collector terminals of both transistor, we are taking the output voltage. And that's why it is known as a dual output or balanced output. Is it visible properly? Is it visible?
Yes, sir.
Okay. Now switch to the second one. It is dual input and unbalanced output. Why it is known as unbalanced output? Because the output is taken out from the collector of first transistor with respective to ground, not with respective to collector of second, like first one. Okay, and that's why it is known as unbalanced. Now go towards the third, single input and balanced output. Now you will observe there is no VS2. That second terminal is grounded, while first terminal it is powered by VS1. So there is only single input. And balanced output means what? The output is taken across the collector of both, not with respective to ground. And that's why such type of output is known as balanced output. And the last one, that is single input and unbalanced output. That means single input and single ended output. You will observe again that VS2, it is replaced by ground, no second input, only one input is there, that is VS1, and output is taken out from the collector of first transistor with respect to ground. That's why it is known as a single ended output, or it is known as unbalanced output. Got it now about the various configurations of differential amplifier? Is it okay? Now, in your syllabus, the analysis for dual input and balanced output differential amplifier is mentioned. So first of all, we'll see the DC analysis. So see, dual input balance output differential amplifier analysis. First one is DC analysis and another one is AC analysis. So for DC analysis, generally we are considering all AC sources as a ground. We done the same in our second unit also, right? We done that DC and AC analysis to find out the quiescent point of MOSFET and AC analysis to find out AV, RI and RO, if you can recall. The same method you have to adopt over here. Okay, means what? For DC analysis, consider all AC signals as a zero or at a ground, right? Just wait a few seconds. Okay, sorry for interruption. So, am I audible? My screen is there.
Yes,
Yes,
sir.
sir.
Okay. So, as that of the AC and DC analysis which we perform related to our that CS MOSFET amplifier, the same analysis we have to perform for this differential amplifier, right? For first one, DC analysis, we will go on to consider all AC sources or input signals, AC input signals as zero or ground. And that's why you will observe, see that VS1 and VS2, which were shown in this case, I grounded it for the analysis, DC analysis purpose. Okay. Then by applying KVL to the input loop, you can take any one, either input of first transistor or input of second, one and the same thing, because it is balanced transistors, or we can say it is a equivalent transistors. So by applying KVL to the input loop, suppose for this first transistor, you will observe RS into IB. RS is nothing but RS1. Okay, current flowing through it is base current of that transistor. So IS into IB plus voltage drop between base to emitter of that transistor, that is nothing but VBE, plus twice IE into RE, that is drop across RE. Okay, and equals to minus VEE. You will observe in differential amplifier there are two DC sources, plus VCC and minus VE. So remember this minus VEE with somewhat like this component, that is RE, it is used for the biasing purpose. In our second unit, you already studied about that current mirror or constant current. MOSFET as a constant current source, right? Now that application I shown. So that circuitry can be replaced by this RE. So this single RE, that means it is not a single resistor. The equivalent of that current mirror or constant current source, it is shown simply for simplicity's purpose, simply by a single resistor RE. Okay. So remember over here, and this minus VEE, it is used for the biasing of this transistor in its active region as long as BJT is concerned. Okay. So it will go on to act as an amplifier when it will go on to bias in its amplifier region, and that biasing is done by using this minus V plus VCC and this biasing component, that is resistor RE. There is no voltage divider, no cell biasing, no feedback biasing. Only by using constant current source biasing, these two transistors are biased in their amplifier region. Okay. So as it is minus VEE, so you have to write it equals to VEE. When you will apply the KVL, we'll start from zero potential, that is ground. So it will be IB into this RS plus VBE plus drop across this RE. Now I will ask one question, from where this 2 came over here? Why 2 is taken? Can anyone? Answer is very simple. If you look it properly, drop across RE, it is taken as twice of IE into RE. Whenever we are applying KVL to this loop, drop across RE is taken as, drop across resistor is nothing but current flowing through it into resistance of that resistor. Here it is taken as twice IE into RE. Why it is like this? Can anyone? No. Okay. So already I told the emitter of both transistors are connected with each other, and commonly it is biased through resistor RE. Right now. So through resistor RE, there are two currents. Which currents? Emitter current of first transistor and emitter current of second transistor. As already I told, both transistors are identical transistor, equal in terms of their electrical parameters or properties. The emitter current will be same. That means IE1 equals to IE2, and that's why simply it is written as IE. It is not differentiated, and hence the total current flowing through RE, it will be twice of IE. And that's why it is written as that drop, or by applying KVL, that term is written as twice IE into RE equals to VE. Okay. Now you might have learned this current relation in case of BJT. Base current equals to emitter current divided by beta DC. Beta DC is nothing but amplification factor of the transistor, as well as IC is approximately equals to IE. Right. Therefore, IE equals to IC, and that will be equals to, if you rearrange all these terms, we are interested in what? This IE will be how much, or IC will be how much. So just by rearranging the term, you will observe that IE equals to IC equals to VEE minus VBE upon twice of RE plus RS by beta DC. Right. Then that VBE, when a transistor is operating in its amplification region, that is nothing but in its active region, then the voltage drop across base to emitter, forward bias base to emitter junction, that is 0.6 volt for silicon if that transistor is manufactured from silicon material, and is equals to 0.2 if it is manufactured from germanium. Okay. Similarly, that RS by beta DC, this term, it is very, very small as compared to twice of RE. Correct? That RS is nothing but internal resistance of input signal. This is the own resistance of that signal source. And that's why that RS by amplification factor of that transistor, it is sufficiently large. So this ratio RS by beta DC, it is very, very small as compared to that twice of RE, and hence that we can neglect, we can omit it, and hence that equation 1, we can write it as IE equals to IC equals to simply VEE minus VBE upon twice of RE. Right? Therefore, I mentioned one statement here. The value of RE sets up the emitter current in transistors Q1 and Q2 for a given value of VEE. The emitter current in Q1 and Q2 are independent of collector resistances of both transistors, that is RC1 and RC2. It is dependent on what? It is dependent on the value of VEE, this negative DC source, as well as the value of this resistor RE. Okay. Means you will observe over here, in the absence of input signal, both the transistors are working in their active region and at the center of that load line, if you can recall. Means we can say that transistors are properly biased. So the biasing responsibility of both transistors, it is taken actually by resistor RE. What is that resistor RE? It is not a single resistor, remember. It is just the various circuits which you studied in the second unit, that is current mirror circuit, constant current source, and all that. That complete circuit, for simplicity's purpose, it is replaced by single resistor. So this resistor RE or that circuits and the applied negative voltage, it will go on to bias both the transistor, or the care will be taken properly. Right? So you have to remember this formula, IE equals to IC equals to, because question may get asked, for the shown differential amplifier, determine its quiescent values of the transistor. Quiescent values means you have to find out the DC values. That means you have to perform the DC analysis. Okay. So knowing the value of IC, the voltage at the collector VC can be determined as VC equals to VCC minus ICRC. It's so simple thing. How much will be the voltage at this collector terminal of transistor? It will be VCC minus drop across that RC. Okay. And VC is nothing but what? Voltage at the collector with respect to emitter. That means VC minus VE. Okay. So you will get that VC equals to VCC plus VBE minus IC into RC. This equation also you have to remember. Whenever you will consider this IC as a ICQ, the obtained VCE, it will be quiescent output voltage of that transistor. And this is known as a DC analysis. Okay. See, one example I taken here, the following specifications are given for the dual input balance output differential amplifier. RC is 2.2K, RB 4.7K, RIN1, RIN2, that is RS1 and RS2 are 50 ohms, plus minus VCC is plus minus 10 volt, beta DC amplification factor, it is taken as 100, VBE, it is mentioned as 0.715, determine the operating point, that is nothing but ICQ and VCQ of both the transistors. I just written that previously derived equations for IC and just put the values that given things over here, and simply you can calculate the quiescent collector current as 0.988 milliampere. Similarly, by using the same previous equation, that is VCE, this one, derived one, you can easily find out the value of VCQ. as long as you will be going to consider this IC as ICQ, that is 0.988 milliamp. Okay, so that the VCQ, it will be 8.54, right? So this is almost about the DC analysis of that dual input balance output differential amplifier. Now we'll switch to AC analysis. Now this AC analysis is slightly complicated as compared to DC. It is somewhat lengthy. Okay, while doing the AC analysis, again same as that of our MOSFET amplifier, whenever we done that AC analysis, what we consider all DC sources as a ground for AC analysis. Okay, and one more thing I highlighted over there while drawing the AC equivalent diagram for the given amplifier circuit, you have to replace all the active elements by their equivalent model. So for MOSFET, that equivalent model you are already familiar right now. Input terminal, gate terminal, it is kept open from the source. Then towards the output side, there is GM into VGS, current source, and its own resistance as small RD. That is the AC equivalent model of MOSFET right now. Here, the transistor considered is BJT and its equivalent model is taken. There are various equivalents. It is not included in your syllabus. So you just have to prepare it directly. Okay. There is various equivalent models, like we can say pi equivalent model, T equivalent model, and all that. And by using that various equivalent models, the AC analysis of transistor, that is BJT, that is active element, it can be done. So in this case, the T equivalent model is considered for the transistor, right? In that T equivalent model, you will observe only single resistor is shown, that is small RE or RE dash. That transistor is totally replaced by this small resistor, that is RE dash, with input as a current source, that is collector current, right? And as per that statement, set all DC voltage sources at 0. What I done, I connected that plus VCC to ground. That means RC gets grounded. For second transistor, same thing. As minus V also get ground. So the same is shown. Now as it is AC analysis, so don't remove these V1 and V2s because these are the AC signals. At V1 and V2, we have to consider as a ground only for DC analysis. But for AC analysis, we have to consider DC sources as a ground. Okay. Now the voltage gain. As IE1 equals to IE2, why we can say IE1 equals to IE2, because it is considered both transistors are identical transistors, right? And therefore their internal resistances, that is RE1 and RE2, these two are same, again equal, and that's why simply it is mentioned as small RE in that T equivalent model of both transistor. Okay. Then the voltage across each collector resistor is shown out of phase by 180 degree with respect to input voltage V in 1 and V in 2, because it is in CE configuration. Now, by using KVL for loop 1 and loop 2, I prepared two loops. For first transistor, that is loop 1 LHS side, and for second one as shown. Okay. So when you will apply the KVL, simply just go through this equation. It is not that much complicated. V in 1 minus drop across this first resistor R in 1, that is nothing but R in 1 into IB1 minus RE into IE1, drop across this equivalent resistor of first transistor into current flowing through it, minus drop across this capital RE. As there are two currents, IE1 and IE2, both you have to consider instead of taking directly as a twice of IE. Okay. Similarly, when you will apply the KVL to the second loop, the same thing you will observe over there. Write it as equation number 1 and 2. Then IB1 equals to IE1 by beta AC That is the relation between emitter current and base current. IB equals to IE by beta. This is the generalized relation. Same will be applicable to second transistor, that is IB2 equals to, again same, IE by beta. Now replace that IB1 and IB2 from this equation, these two, by that IE1 by beta AC. So you can rewrite that above two equations like this. Again, generally that IN1 by beta AC values are very small. Therefore, again we can replace it by, or we can omit it. Okay, and hence you will observe that the remaining equations will be small re plus re1, capital RE in bracket into IE1 plus RE2 into IE2 equals to V in 1. When you will go through it, when you will do by yourself, you will get clear idea about it. It is not that much complicated. Okay, you just have to keep in mind the relation between base current and emitter current in terms of beta AC as well as in terms of beta DC, and you just have to replace few steps. Okay, now see, you will have these two equations 3 and 4, equation number 3 and 4 for V in 1 and V in 2. Okay, in terms of that IE1 and IE2. So by solving these two equations using Cramer's rule for IE1 and IE2, you might be familiar with this Cramer's rule. It may be either in M1 or M2 or in M3. You might have studied it. Okay. So by using that Cramer's rule, you can easily find out IE1 and IE2. Okay. Just go through these steps. Mathematical steps are there. Using that Cramer's rule, you can easily find out that IE1 equals to this much, IE2 equals to again almost this much. Okay, the output voltage is VO equals to, as it is a balanced output, that means the output voltage, it will be across the collector of both transistor. That means it will be the difference between VC2 and VC1. Hence, I written here that VO equals to VC2 minus VC1. Correct? And what is that VC, collector voltage? That already I mentioned in the previous slide. That is nothing but RC into IC. Okay. So that you will get that VO equals to RC in bracket IE1 minus IE2. Now substituting the current relations IE1 and IE2 in this equation number 7, you will get that VO equals to, and at the end, how much you have to remember that VO equals to, see, capital RC by small re into difference between that two inputs, that is V in 1 and V in 2. So how much will be the output of this differential amplifier? It will be equals to capital RC by small re into difference of V1 and V2. That is V in 1 minus V in 2. This is the important equation. That is for VO. So you will observe that output voltage of differential amplifier, it is dependent on that capital RC and small re. Okay. And here I mentioned thus a differential amplifier amplifies the difference between two input signals by defining VID, that is nothing but equals to V in 1 as the difference in input voltages. We can write the voltage gain equation of the dual input balance output differential amplifier as follows. AD equals to VO by VID. It is simply capital RC by small re. So question will get asked, find out the differential gain, that is AD. So while determining that AD, you have to consider only this much ratio, that is capital RC by small re. Right? For input and output impedances, again there is derivation, but I directly written that Ri1 equals to Ri2. Purposely I written it directly equals to, because as the transistors are considered as identical, the input impedance of first will be same as that of second, and that is again directly equals to twice of that AC amplification factor into small re, and output impedances of both that will be directly equals to capital RC, right? So only these 3 to 4 formulas you have to remember so that you can directly solve the given numerical, right? I taken one numerical for the reference. See how it will get asked. The following specifications are given for the dual input balance output differential amplifier RC 2.2K, same previous numerical. I just taken the consider the previous numerical, that is where we done the DC analysis. Okay, but over here you have to determine voltage gain, input impedance, output impedance. That means you have to perform the AC analysis. So the AC emitter resistance, you have to remember this formula directly. That AC emitter resistance, we replace that BJT by its T equivalent model, where that small re is mentioned. So how it is determined? Simply it is volt equivalent of temperature divided by IE, emitter current. Volt equivalent of temperature value of that VT is 25 millivolts divided by IE. Now, as we mentioned that IE is approximately equals to IC for BJT, and that IC we already determined in the previous numerical. That IC was 0.988 milliamperes. So simply you can easily determine the value of this small re. So that small re equals to VT by IE, as IE equals to IC. Therefore, you will get that Re equals to 25.3 ohms. And remaining now, it's very simple. As already I highlighted that AD equals to capital RC by small re. So capital RC is 2.2K, small r is 25.3. So you will get that differential gain of this differential amplifier as 86.96. Ri equals to Ri2, Ri1 equals to Ri2 equals to twice of beta AC into Re. Just put the values, you will get the value of that input impedances as 5.06 kilo ohms. And similarly, output impedances RO1 and RO2, as it is mentioned as RC, and that will be equals to 2.2 kilo ohms. So that was about completely